So A is a 3x4 matrix. So I always find it helpful to sort of build myself a picture of what's going on. So 3 rows, 4 columns. So there's my matrix A, right? 3x4 matrix. So col A is a linear combination, it's a set of all linear combinations of the columns. So if you take linear combinations of each of these columns, like throw a scalar on each column, add them together, you're going to live in R3. Yeah, because these columns all have 3 entries. Take a linear combination of them, you're going to get a 3-entry vector as your result. So this one's R3. And then the null space, that's the set of all things that you can multiply A by to get the 0 vector. So if this is 3x4, then the vector that you can multiply would have to be 4x1. So null A lives in R4. And what ensures that a basis is the smallest possible spanning set? So yeah, there's the definition of a basis. It has two pieces. It has to span, it has to be a spanning set, and it has to be linearly independent. Okay, so 4.3 is about the concept of a basis of a vector space. So I'm going to jump over the first bullet. A set of vectors forms a basis for a vector space if the vectors are linearly independent and the vectors span the vector space. So that means that a basis is a spanning set that is as small as possible. So if you take the span of your vectors, you generate every vector in the space, but you want that set to be as small as possible. And to make that happen, you need it to be linearly independent. So there's stuff about pivots and rows and columns, right? Remember that linearly independent happens when there's a pivot in every column, and the columns span the space Rm if there's a pivot in every row. So to have a basis, you're looking for a pivot in every row and every column. Okay, so I've got 2 vectors here, v1 and v2. Does the set v1, v2 form a basis for R3? So I'm asking 2 questions. If I want to know if something's a basis, I want to know, are the vectors linearly independent, and do they span the space, in this case R3? Okay, so I'm looking v1, v2, span R3, and linearly independent. So checking 2 things. So we put them in a matrix, we row reduce, and get 1 0 0 0 1 0, right? So this is linearly independent because there's a pivot in every column, but it does not span R3, right? So this means that there are elements of R3 that you cannot build by taking a linear combination of V1 and V2. It's not a spanning set. So it's not a basis, right? It has to be both things. It's linearly independent, but it doesn't span R3. So not a basis. How about, does it form a basis for R2? Yeah, I'm getting some blank stares, and that's because it's a question that doesn't make sense to ask, right? You can't possibly span R2 if the vectors live in R3. Okay. So this one's definite no. All right, so now I have a set H. So I've described it in set builder notation. It's just the set of all vectors that look like a real number, 0. Okay. And I want to describe this with a basis. So a basis is a spanning set that's linearly independent. So I need to come up with a set of vectors that when I take linear combinations of them, I can build every vector in H. And the vectors that I choose need to be linearly independent. So let's just want to rewrite this as the span of some stuff. So I've got an S and a T, so I could have 1, 0, 0, and 0, 1, 0. Right? If I throw a constant on this one and a constant on this one and add them together, I'm going to get real number, 0. Right? Oh, I just moved it. That make sense? So because 1, 0, 0 and 0, 1, 0 are linearly independent, that is a basis. So basis for H is just the set 1, 0, 0 and 0, 1, 0. All right, so the definition of a basis is just a spanning set that's linearly independent, smallest possible spanning set. So because the null space of a matrix and the column space of a matrix are vector spaces, we can talk about finding a basis for those spaces. Smallest possible spanning set for each of them. So last class, we already were able to find spanning sets. So we did that already. We were able to describe the null space of A by writing it as the span of some vectors. And it turns out the method that we use when we find the null space of A and you describe it in parametric vector form, and then you take those vectors from parametric vector form, those will always be linearly independent. So we have nothing new to learn here, right? If you want to describe the basis for the null space of A, you do exactly what we did before. And you augment with 0, 0, 0. Just going to draw it up here. Row reduce, and I get 1, 0, 0, 0, 1, 0, 6, 5 halves, 0, 5, 3 halves, 0, 0, 0, 0. So if I translate this to equations, it says x1 plus 6x3 plus 5x4 is 0. And x2 plus 5 halves x3 plus 3 halves x4 is 0. And then my bottom row is just 0, so I don't have to write that down. And then my free variables are x3 and x4. So to write my solutions, I've got a vector for each free variable. And x1 is negative 6x3 minus 5x4, right? I would just solve for x1 there. x2 is negative 5 halves x3 minus 3 halves x4. x3 is free, and x4 is free. These two vectors are a spanning set. Right? So this is the span because this is just the definition of span as a linear combination. Put a weight on each of them and add them together, which is exactly what's written here. X3 and X4 are your weights. You add them together. So this is what we did last class. It turns out that this spanning set is also linearly independent, always, when you do this process. So this is also how you find a basis for the null of A. So it's just these two vectors. Yeah, so when you're writing a basis, you don't have to write the word span, because the word basis encompasses the fact that if you take the span of them, you get the whole space. All right, finding a basis for call A is has one more step than what we did before. When you want to find a spanning set for call A, you can just list the columns of A, right? Because that's the definition of the column space, is all the linear combinations of the columns of A. So the columns of A, by definition, form a spanning set. But if one of those columns of A is a linear combination of the others, you can remove it and still have a spanning set. So you want to like narrow down the spanning set until you have a linearly independent set. So the way you do that is you identify the pivot columns of the matrix A. So by row reducing, I now know that column 1 and column 2 are the pivot columns, right? So all I need are column 1 and column 2 to span the column space. The other two I can drop because I can build both of them as linear combinations of the first two. If you take the linearly independent piece of the set, you can build the other two and you don't need them. So I just need columns 1 and 2 from the columns of A, and that would be my basis for the column space. Just the pivot columns of the original matrix: -2, 2, -3, and 4, -6, 8. Just make a note. Those are pivots of original A. So you have to do the row reducing to identify the pivots, but then you have to remember that you take those columns from the original matrix A.